So a few more words about special relativity. I want to introduce the standard notation of 4 vectors using the example that we've seen for the Lorentz transformation that we have. So let's just do some standard notation. We're going to use coordinates with upper indices that are defined in the following way. So first of all, there's a time-like coordinate, which we'll define as speed of light times time interval. We're going to use a handy little factor, which is v over c, where v is the relative speed between the 2 frames of reference that we're considering. And then the other coordinates we will, identify like this. So what was before y is just x with index 2, and z is going to be x with index 3. Like this. Okay, it's just notational convenience. Now the point is that we can write our transformation, so the Lorentz transformation, in the following way. We will say that x bar 0 is equal to gamma times x0 minus beta x1. We have x1, x bar 1 is equal to gamma x1 minus beta x0, and for the other two they're just unchanged. X bar 2 is equal to x2, x bar 3 is equal to x3. Now the nice thing is that we can express this in matrix form. So I'm going to arrange the barred coordinates into a vector. And now I'm going to arrange the original coordinates in a similar looking vector. And because the relationship between the 2 sets of coordinates is linear, I can write this as just a simple matrix acting on the other bit here. So first of all, the 2 and 3 coordinates, they transform as the unit, like this, unchanged. The other coordinates, so there's no coupling between these blocks here. And now only the x0, x1 have a non-trivial relationship. You see on the diagonal, I have a gamma. And on the 1, 2, 2, 1 or 0, 1, 1, 0 elements here, I've got minus beta gamma, or minus gamma beta to follow the notation in the book. Okay, so this is very convenient because we will rewrite this compactly as the following thing. So we will have the barred coordinate with a certain index mu taking values between 0 and 3. This is going to be the summation for a subsidiary index nu from 0 to 3 of this transformation matrix that we will write as big lambda mu nu with x nu. Okay? And just as a further simplification, there's a summation convention that was introduced by Einstein that says that each time you meet a repeated index, which is up and down, then you sum it over. Okay, so by definition, this would be written like this. Where on the right-hand side here, the summation over the new index is implicit. Okay, bit of nomenclature. So 4 vectors, 4 vectors, obvious why we call them 4 vectors. So 4 vectors with an upper index. They're called contravariant. Four vectors. And 4 vectors with lower indices, they're called covariant. Okay, The scalar product in relativity, so scalar is defined as the in product between covariant and contravariant vectors. Okay, let's just say we have two of them. I'll do this in this order. I will say that the summation over mu of A mu B mu, so that's again written as A mu B mu, where the and of course it's going to be equal to also just going up and down with the indices on the pairs here, where we've defined the vectors with the lower indices as a simple linear transformation. So here I'm adopting the summation convention, okay, where this G mu nu is a matrix that represents, if you want, the signature of space-time. It's the diagonal matrix with zeros everywhere except on the diagonals, but a different sign for the time-like component. Okay? So this is known as the Minkowski metric. Okay? So the point of introducing scalar products of covariant, contravariant vectors like this is that this generalizes the notion of the norm of a vector. Okay? And there's an idea in special relativity of invariant intervals. Okay? Because under Lorentz transformations, the scalar product between objects doesn't change. And if I look at a certain 4 vector, A mu, I can consider its norm, so A mu, and this can take different values because of the signature here of time being different in sign from that of space. The value of the norm doesn't have to be positive definite. It can take both signs, and there are different cases here. So if the norm is greater than 0, then the space components dominate over the time components, and this is called space-like. If, on the contrary, the norm is less than 0, then the interval is called time-like. Okay, and then if it's equal to 0, although this term is not used very often, this is called light-like. More often people say that you just stay on the same light cone. Okay, so let's now say you have two events. A and B. Then the difference delta x mu, by definition, just the component-wise difference between the coordinates, okay, this is called the displacement for vector. Okay, and its scalar product with itself okay, I'll write it like this, I, which is just by definition the scalar product of delta x mu with itself, okay, if you look at what that is in the coordinates we've chosen, it's just minus c squared delta t squared, if delta t is the time interval between the events, and then the norm of the actual space vector between the events, okay? The important thing is that this is an invariant under Lorentz transformation. Okay, so these are just basic basic notions that that you probably have all seen in the first year, but that we'll just use a little bit as we go further. There's a bit in the book about drawing these Minkowski diagrams. You know, you just write these space-time diagrams like this, where essentially you put the you know, world line of the photon at 45 degrees in the original. Okay, so this is like a photon traveling here. In these diagrams, you kind of put the coordinate here and the time here. So anything moving at velocity less than the speed of light would follow a line like this. Now, the point of these diagrams is that it really allows you to visualize very well what is connected with space-like or time-like intervals or light-like intervals. It can also give you an idea of which sets of points you could view as being simultaneous in a particular reference frame, and then not necessarily simultaneous in a different reference frame. It tells you what kinds of configuration of points you can also reach under various Lorentz transformations. If you do Lorentz transformations like we've seen here, you're actually always conserving these scalar products here, and that's just the formula for if this is equal to a certain constant, then you just have a surface in this four-dimensional space that's defined by the constant value that this takes. You know, just like a hyperboloid of revolution they have here. You have space-like ones and time-like ones. But I guess you've seen most of these in the first year, and we're not going to make very much use of this for now. So I'll just leave it at this for now.